Section 3.5, we're going to take a look at multiplication and division algorithms. We're also going to do some more with estimation and with mental math in this section 2. But we're actually going to start at what kind of feels like a little bit of an odd place to start. And we're going to start with exponents. And we explore exponents in a couple of different sections in this book, and this is one of them. Another one of them occurs when you take proportional and statistical reasoning. So exponents, a to the n means to multiply a by itself n times. And we've already seen that definition once. We saw it when we looked at geometric sequences, okay? This is for a rational number a. A is called the base, and the number n is called the exponent. And what we're going to do is we're going to talk about some of the properties of exponents and how those relate to multiplication. So what you'll notice on the first one is that you have the same base, a. The exponents could be the same, but they wouldn't have to be, so they're represented as m and n as being different. The question is, what happens when I multiply a to the m times a to the n? Does anybody remember? Yeah, that's right. Good job, Maggie. So same base, a, all right, doesn't change at all, still a. And we add the exponents together, m plus n. I'm going to talk to you a little bit more about why that happens later. But number 2 is actually quite similar. If when we multiply, we end up adding the exponents, what do you think will happen when we divide? When we subtract. Thank you, Veronica. So we have a to the m minus n. Notice the base stays put, stays the same, never changes. It's a. And it's true if it's a number, right? If it's 2, it's 2, it's 2, it's 2. It never changes to, say, 4. Just doesn't happen. The base stays the same. Number 3 is an exponent raised to an exponent, right? So we've got a to the m, and then it's raised to the power n. What do you think you might do with this exponents? We multiply them. That's exactly right. Good job, Hannah. So this is m times n, or we can just write them m n beside each other. And the fourth and final one that we're going to take a look at for the time being is ab to the m. So we have a times b, and it's to the power m. And I hear people use the phrase distribute. It's not exactly what's going on here, but I know why you think that. This actually ends up being a to the m times b to the m. So in some sort of a fashion, we see the m crossing across the parentheses and applying to each of the variables individually. Notice that's happening because the variables a and b, those two numbers, actually they're numbers, but that those two values are multiplied. If they were subtracted or added, this property just simply wouldn't be true. Okay, it's because they're multiplied. All right, I would like to show you, I can't remember if I've got it on this side. Yeah, it's on the next slide. How and why each of these actually work. Okay, there's only 4 of them. They're not terribly difficult to actually justify why they work. These are not really like proofs, you know, like in geometry, you're like proving that it's true for all values kind of thing. That's not what I'm doing. I'm not proving that they're true, but I am trying to justify why they make sense. And I think that for the purposes of the kids that you're working with, if you are trying to do this, a justification for why it makes sense is usually good enough. To answer the question of, but why, Ms. Para, right? Like this, well, why, but why? And you're like, okay, I got to know a reason why. This is a pretty good way of being able to justify the why. All right, so on the first one, we already said that this is adding the exponents together, right? That's the property that we're trying to justify. And I'd like to give you an example showing why that it works with some numbers that are m and m that are pretty small. So we're going to do a to the 3 times a squared. And what we're going to do is we're going to sort of distribute them all out, like simplify them down to all their like lowest denominator pieces, like all their little pieces, and then see what happens. So what does a cubed mean? Right, it means a times a times a, so that's this piece. And then what does a squared mean? It means a times a, so that's the second piece. And you'll notice if you set them all beside each other and you count them up real quick, how many a's do you have? 5. So this is a to the 5th. And pretty quickly you can see that what happened, numerically speaking, is that I started out with a 3 and a 5, and I'm sorry, 3 and a 2, and I ended up with a 5. So how did I get there? I added the exponents together. Again, it's not a proof, because the proof would have to show this true for all values of m and n, right? And I just showed it to you for one value. But it's a pretty good justification that it makes sense. Let's do the second one. We said that this is supposed to be subtraction. And the example that I'm going to do is going to be a to the 4th over a to the 1, or a to the 1st. All right, so a to the 4th means what? Okay, a times a times a times a, and a to the 1st is simply a. Okay, so before you would ever get to looking at exponents in this fashion, there's going to be fractions that are going to be discussed, and simplifying fractions and things like that. Or you could talk about this in terms of division itself if you were working with numerical values for a. And very quickly what happens is you see this a canceling with one of these a's. I don't care which one of them. And how many a's are left on your problem? 3 of them. So it's a cubed. And again, we can talk about how do we get from the 4 and the 1 to the 3. Well, we subtract, as opposed to, say, maybe trying to divide, right? A common mistake here would be a kid would be saying 4 divided by 1, I've got 4, right? But I don't end up with a to the 4th here. I end up with a to the 3rd, so it's a subtraction property. All right, our third one, Hannah told us this one was multiplication, and she was right. So we're going to do an example on this one that's going to look a lot like our number 1 problem, because people get number 1 and number 3 confused very easily. Those two are easily confused, frequently confused even. So on number 1, I did a to the 3rd times a squared. On this one, I'm going to do a to the 3rd squared. Now, earlier, you've all told me that a to the 3rd is like this, right? That's a to the 3rd. And squaring something means multiplying it by itself. So here's 2 pieces multiplied by themselves. It's a to the 3rd times a to the 3rd, right? And again, if you count all these up, how many a's do you have? 6 of them. So how do you get from 3 and 2 to 6? You multiply. Our last property that we're looking at has this sort of a distributing feature or feel to it. And we said that AB to the M is A to the M, B to the M. And the example I'm going to do is AB to the 3rd. So multiplying something to the 3rd, or raising it to the power of 3, means multiplying it by itself 3 times. Now, we encountered some problems back in, I think it was section 3.3, where we had something kind of like this going on. We didn't have this many things, but it was like this, where the answer then required us to switch parentheses around and to flip A's and B's around. I did one on the board that was like that. And we looked at what properties were present. And the properties that kept coming back up over and over again were the associative property, right, regrouping parentheses, and the commutative property, which was switching the letters themselves around. And if you did enough of that, switching the letters around and regrouping the parentheses, you could eventually get to all of the A's being together and all of the B's being together, right? I mean, just the application of the commutative and associative property over and over and over again. And when you did that, you would eventually recognize then, of course, that there are 3 A's and there are 3 B's that are then regrouped. So it's A cubed, B cubed. So, okay, keep in mind why I'm showing you this. I am not showing you these 4 pieces right here because I ever expect you to show them to me again. That's not what the point was, okay? In fact, I won't. I won't ask you on the test, prove to me why this worked or justify why. That's not my question, okay? We're going to use these properties as given information, as discovered or learned information. So if I ask you this problem over here in a minute, right here, we're not expecting you to somehow go through writing out all the 6s and all the 2s and all the 3s and to regroup. That's not the point, okay? Somebody already did that. In fact, you and I already did that on these previous slides. Okay, our point is to be able to use the results, but then when you're in your real teaching situations and little Joey says, but why? Even if you can't remember it right off the top of your head, you can know, I saw a but why, and I know the but why. I may need to go look it back up again, and when I see it again, I'll remember it because it was explained to me before. Does that make sense? Okay, so let's take a look at these problems. Now, keep in mind, every single one over here, all these rules over here or properties over here had the same basis. They were all A's, right? And the very first problem doesn't have that. So we got to be able to deal with that issue and see what to do about it. One of our bases is a 6, one of our bases is a 2, and one of our bases is a 3. Everybody good with that? Now, we haven't talked about primes and composites, but I know you know about prime and numbers. 2 and 3 are prime numbers. We'll talk more about them in chapter 4. 6 is not a prime number. 6 can be broken down. How can 6 be broken down and multiplied? If it was multiplication. It's 2 times 3. So, I'm sorry. No wonder you're looking at me crazy. I was on my screen wrong. Let's go back to A, where they're all the same first. I'm so sorry. Oh, goodness. That's what happens when you zoom out too much on your screen is you lose track of where you are. Let's go to number A, or letter A. All right, these are all the same, 5, 5, 5. Fantastic, so we can use our property as is. There's 3 of them there, but that doesn't change anything. 3 of them being present is just like when 2 of them are present. All the bases match, so what can I do with all these exponents? I can add them, that's right. So 10 plus 2 plus 4 would be 16. And that's our final answer. Okay, your calculator is really of little use on this problem because if you try to put it in, you're going to have the 5 to the 16 where it turns it into scientific notation. It doesn't keep it in the exponential form that makes any sense. And that's going to be the case on many of these. Okay, back to what I was trying to explain with my 6. Let's do my 2 and my 3. So we're going to take this and we're going to break this down into 2 times 3. I'm going to show you 2 ways to do this problem. This is our first way. Okay, is everybody good so far? Okay. That wasn't a property of exponents. That's just a property of the number 6. It's 2 times 3. There is a property of exponents now happening with the parenthesis part that I just sort of inserted. What can I do with the 2 times 3 that's raised to the power of 4? Right. I can break this apart to being 2 to the 4th times 3 to the 4th. And I still have a 2 cubed times 3 cubed here, right? And once I do that, I actually have some pieces now that have the same base. I have a 2 to the 4th and I have a 2 to the 3rd. What does that give me? 2 to the 7th. I also have a 3 to the 4th and a 3 to the 3rd. What does that give me? 3 to the 7th. This is one perfectly reasonable answer. It happens to have prime numbers as the bases. Another perfectly reasonable answer here would be that this is 6 to the 7th. So let me talk about why or how you would get from that one spot to the other spot, and then I'm going to show you another way completely to do the problem. If you'll notice, both the 2 and the 3 have the same exponent, and you could sort of undistribute, right, pull out the power 7, and then you'd have the 2 times 3 that would give you the 6. So this would be a second perfectly reasonable answer and perfectly correct answer to the problem. Now, one other way to do this problem, instead of factoring here, right, taking the 6 and breaking it down into 2 and 3, is we could have left the 6 as 6 to the 4 and recognized that this 2 and this 3 here could be multiplied with the power 3 being pulled out at that point. If you saw it that way, here's my 6 to the 4th, and then I'd have a 6 to the 3rd, I would then get same bases this way. And then 6 to the 4th times 6 to the 3rd would be 6 to the 7th. Okay? So that's another way to arrive at one of the 2 reasonable solutions as well. Okay, so sometimes we have to be okay with the fact that more than one answer is still okay. This is one of those places. Any questions on this one? Okay, so the reason that exponents are included in this is because it's repeated multiplication, right? It's a way of simplifying repeated multiplication together. The next thing we're going to shift to then is our actual multiplication algorithms. So, our multiplication algorithm, the first one that's listed is called the standard algorithm. The expanded standard algorithm. And with the expanded standard algorithm, what we do is we break down the 48 into 40 plus 8. And we break down the 32 into 30 plus 2. And then what we're trying to do is we're trying to get every combination of multiplication. So the order doesn't really matter so much as long as you get them all. So here's two of them, 2 times 40 and 2 times 8. So I'm going to write those down. 2 times 40 plus 2 times 8. And then let me change colors to get the other two just to differentiate. I'm going to have a 30 times 8 and a 30 times 40 in whatever order you'd like. So plus 30 times 8 plus 30 times 40. So we're expanding the number 48 into 40 plus 8. And then we're doing all 4 types of the multiplication, or 4 pieces of the multiplication that are really present. What is 2 times 40? 80. 2 times 8? 16. 30 times 8, 240, and 30 times 40. I think it's 1200. We get 2 zeros? 1200? Okay, good. And if you don't like doing this sort of linearly, like written across the page like that, you could write them out this way too. So like you could write 2 times 40 plus 2 times 8, and then, you know, the answer's over here. So this is 80 and 16. We could add them sort of vertically instead. Doesn't make any difference. It's just another visual picture of how it could be written. Adding these together now, we have 80 plus 16. You can add them together 2 pieces at a time if you'd like, or we could go back to adding them where they're all written out for us like this. 1200. Sorry, I guess I should start the way I did it before. 80, 16, 1200, and 240. 240 and 1200. Well, okay. I think y'all are okay. These are our 4 numbers. At this point, you can add from left to right or right to left, depending on what you want, which method you want to use. Let's just use the standard algorithm. I've got a lot of zeros in the ones column. That's a 6, and 3 zeros, so 6. 8 plus 1 is 9. 9 plus 4 is 13. So write a 3, carry a 1. Careful, because I got a lot of zeros here. I've got 1 plus 2, which is 5, and then my 1, so it's 1536. So the expanded algorithm is simply expanding the numbers, multiplying and adding. The next algorithm is a variation of this. It's a little bit more structured and a little bit better visually for kids. It's called the partial products algorithm. We're still going to break the 40 apart into 40 and 8. But we're going to draw it in a rectangular way. So I have a box here. This isn't lattice, but it kind of starts feeling like it a little bit. I have the 40 and I have the 8, and then I have the 30 and I have the 2. And you write it along the top and along the right hand sides. And we're just multiplying the length and the width in the box. So for instance, if you have 40 times 30 in the first top left-hand corner, that's that 1200 you guys told me before, and it would go right here. 8 times 30 is the 240, and it would go in the top right-hand corner. 40 times 2 is my 80 in the bottom left-hand corner. And then 8 times 2 is the 16 in the bottom right-hand corner. And you would add all the boxes together. And of course, it would still be the 1536. Now let me actually talk about where this is coming from as an argument for why it works. If you were to actually draw a very large box, this will work better. What were numbers? Okay, let's go like this. And if you were to take the number 48 and you were to break it apart as like this whole length is 48, you could actually break it apart pretty reasonably into this piece is 40 long and this piece is 8 long. Does that make sense? Like it's actually like measuring the side of the box, like an area diagram would. And then the number 32, you could break it apart. It would be really small by comparison, but here's 30 and here's 2. And you can actually see where the length and the width are coming from, right? So the length of the top left-hand corner box is 40, and the width is 30. So 40 times 30, this is why this is huge, right? Because it's 1,200 compared to down here in the bottom right-hand corner, this is 8 wide and 2 long, or vice versa, whatever, and it's only 16 units instead. You could even draw in a grid if you wanted to really emphasize where all the values are truly coming from, right? Think about a grid like if you had kids draw it on like a dot grid paper or graphing paper, you could draw this out, right? So that's where this is coming from, partial products. This one, in terms of intuitiveness of explanation, is my favorite explanation. This one makes the most sense, I think, to work with. The next one's called the lattice algorithm, and we've seen lattice algorithm for addition already. So now we're going to do the lattice multiplication algorithm. I had one of my math method students who's working with a child who all he ever learned was the lattice algorithm for multiplication. And there's nothing wrong with that per se, but it became quite difficult as he moved on to use that algorithm to do multiplication with decimals and things like that. And so she was working with him on learning some other algorithms to be able to accommodate that. My daughter, when she was first learning the standard algorithm, it just wasn't clicking. I showed her partial products, and then that didn't work very well for her either. And most of the time, math comes very naturally for her. It's a very easy subject for her. When I showed her lattice multiplication, bam, she was good to go and no problem. And she picked up the other algorithms later. So it was just a matter of this made the most sense to her off the bat, and then she developed into the other ones, which were more efficient later on. So let me show you this algorithm. We're going to do it much like we just did the other one with the boxes. So it's a 2 by 2 number, so you need a 2 by 2 box. Okay, and so when I say 2 by 2, it's because it's a 2-digit multiplication times a 2-digit multiplication. Instead of breaking the number 48 into 40 and 8, we actually break it into 4 and 8. So you're just writing the single digit parts of it out, and the 32 into 3 and 2. Now, on this one especially, your numbers need to go on the top and on the right. Over here, your numbers could have gone on the bottom and on the left for all it really mattered. It really didn't matter. But over here, for what we're going to continue doing the problem, they do need to be on the top and on the right. Okay, that's important. And we're going to cross-hatch or put diagonals in, just like when we did lattice for the addition. Okay, so cut all your boxes in half. And we're going to multiply each box out, length and width kind of thing. So we have a 4 on the top left, and we have a 3 on the top right. 4 times 3 is 12, right? 2-digit number 12. So the 1 goes in the top box, or top half of the box, and the 2 goes in the bottom half of the box. And this always it works because it's always a single-digit multiplication, and the biggest single-digit multiplication, which would be 9 by 9, is 81. So you never do 2 single-digit multiplications and get a 3-digit number. Like, that doesn't ever happen. So this always will fit in the boxes. 8 times 3 is 24, so the 2 on the top and the 4 on the bottom. What's 4 times 2? 8. So that's a single digit, right? That's okay. It just means that the single digit goes in the bottom of the corner. And if it helps you to sort of think about it, you're welcome to put a 0 in this top box, or you're welcome to leave it blank either way. And then we have one more box. It's 2 times 8, which is 16. Yep. So 1 on the top and 6 on the bottom. One of the nice things is that you can fill the boxes in whatever order you like. So if you want to move from the top to the bottom, if you want to move from left to right, you can do that. However, just like with the lattice addition, after you have the numbers filled in the boxes, you do have to move from right to left. So you need to extend your diagonals. Okay? And you start with the bottom right-hand corner. That, in this case, is a 6. So we're going to write down the 6 because it's addition. We're only adding up values that are inside the box. Don't get confused with your stuff that's residing outside the box. That has nothing to do with your sums, okay? On the next diagonal, I have 4 plus 1 plus 8, which is what? 13. So I write down the 3 and I carry the 1 over here. And now I have 1 plus 2 plus 2, which is 5. And then going one place over again, I have a 1. And my solution then is 1536. Both of the algorithms, well, I've shown you 3 algorithms. All of the algorithms I've shown you so far don't have to be 2-digit by 2-digit multiplication. They could be 2 digits by 3 digits or 3 digits by 3 digits. They could get larger, okay? I always think it's interesting how far people really want to go in school and teaching multiplication and how far out they go. But sometimes they go pretty far, right? I mean, I know my kid was doing 3-digit by 3-digit multiplication, and that takes a while. And I remember seeing her do some 4-digit stuff too, and I thought, really, 4-digit multiplication isn't necessary to gain the understanding of what you're doing. But some of your curriculums will still be doing that. And so this is not so bad. Because if you were doing a 3-digit by 3-digit multiplication, you're just going to get a 9-grid square, right? That's all you're going to get. But if you're doing the 9-digit by or 3-digit by 3-digit multiplication with a standard algorithm, it's going to be long and ugly too. So I don't know that this is really longer or uglier than the standard algorithm necessarily. But it confuses people because their parents have never seen it. So just imagine that you send this home with the 7-year-old that's in your 1st grade class or 2nd grade class or whatever, and mom and dad have never seen lattice multiplication before. Are they going to be freaked out and frustrated at you? Probably so. So as you look at and work with algorithms that are maybe not what you learned or maybe not what you think your parents of your kids have learned, probably be a good idea to, I don't know, send home in the newsletter, we're doing this different method. You know, if you have any questions, contact me, or show them an example or something so that they're not frustrated at you because you're trying to teach them something that their kid doesn't need because they never learned it. It's a real common problem for parents and teachers to have, is that disconnect. All right, let me show you a couple of division algorithms next, and then we will pause for today. All right, yeah, we'll do 2, or do you even want to? Yeah, we'll do 2 division algorithms and we'll stop there. All right, so the first division algorithm is the standard division algorithm that you know and love, and it relies very heavily upon whether or not you know the multiplication facts that you're dividing by. So this is division by 5. Most of us know our 5s tables. Oh, I put the number 5 at the end. Thank you. Okay. Most of us know our division by 5, or know our multiplication tables for 5s. And that's good. Not all your kids will, because they may have learning disabilities or something like that that prevents them from doing this. But this method really relies heavily upon you knowing your multiplication facts. So for instance, you probably looked at this and you said, how many times does 5 go into 6, right? And that one's not too bad, and you knew it went in 1 time, and you said 1 time, and you said 1 times 5 is 5, and then you subtracted, yes? Then you brought the number 2 down, so now you have a 12. You have to ask yourself, 5 times what? How many times does 5 go into 12? And the answer is 2. So 2 times 5 would be my 10. I would subtract and I would get a 2. And then I bring my 3 down. You don't have to draw the arrows, but I know a lot of people do like to draw them. So if you want to draw them, by all means do. 5 into 23, how many times? 4. And sometimes it works out nice and even, and sometimes in less problem, like in this problem, it doesn't. And you end up with a remainder. And when you're first learning multiplication, division kind of stuff, you write R3 at the end, right? So my answer is 124 R3, 124 remainder of 3. Like for the answer, you mean? Yes, you'll have that as your answer, exactly. Now, one of the things to keep in mind here is not only do we have to worry about does the kid know their multiplication facts, but division eventually will be division by values that you don't know multiplication facts for. Like, I don't know my 15s tables. I can generate them not too very badly, but if you get to 17, it becomes much more difficult in my mind. And especially more difficult when you have 2-digit numbers where the second digit's large, right? Like if I divide by 21, it's almost like dividing by 20, and I'm good. But if I divide by 28, that's a lot harder, okay? So this other algorithm that I'm going to show you has drawbacks and it has benefits, and this is called repeated subtraction. Now, you guys saw repeated subtraction in a very simplified case when we did it in 3.3. This is for a bigger case. There's more going on. And I don't know about you, but I don't want to subtract 623 minus 5 minus 5 minus 5. I don't want to do that 124 times, okay? So let me show you how it looks when the numbers are bigger. We have our 623. And what we're going to do is we're going to try to subtract the biggest 5 followed by zeros possible. Okay? So I can subtract a 5 from the 6, correct? So I'm going to subtract, in this case, it's 500. So where does 500 come from? Well, it's 5 times 100. So our goal in doing this is always going to be 5 times a power of 10. So 5 times 10, 5 times 100, 5 times 1,000, 5 times 10,000. It'll always be 5 times the power of 10. And I'm able to subtract the 500 here. And so again, if I were like dividing by 28, I'd be able to subtract 280 or 2,800 or whatever, right, pretty quickly. Because I just multiplied by 10, or I multiplied by 100, or I multiplied by 1,000. So this is 123. And can I subtract 500 again? No. So now I move down into 5 times something smaller, and I can do a 5 from the tens place, right? 50. That's 5 times 10. So what's 123 minus 50? 73. I have 73. Can I subtract 50 again? Yes, I can. So minus the 50, which is 5 times 10. Please do write out the 5 times 100, 5 times 10s. We're going to use them in a minute. 73 minus 50 is 23. Can I subtract 50 again? No. So the next thing and the only thing I have left to be able to do is to subtract 5s, because there's no 5 with zeros that I can still subtract. This is actually the same as subtracting 5 times 1, and 1 is actually a power of 10. It's a weird power, right? 10 to the 1, or 10 to the 0, but it is a power. So what is 23 minus 5? 18. I'm running out of space, but I can just move over here. Can I subtract 5 again? Sure. It's 5 times 1. 18 minus 5 would be 13. Can I subtract 5 again? Yes. 5 times 1. 13 minus 5 is 8. Can I subtract 5 again? Yes. Am I a broken record? Yes. I'm about to be not a broken record, though. 5 times 1. 3. Can I subtract 5 again? No. I'm done. There's no more subtracting because the number's smaller than the divisor at this point. So the question you should be asking yourself is then, okay, fine, I got down to 3, just like the remainder of 3, but where's my answer? My answer is in all the numbers that I added, or that I subtracted when I multiplied them by 5. How many hundreds are there? There's 100. How many tens? 2 tens. I've got 20. And how many ones? 4. I just add them up. There's 100, 20, and 1, 2, 3, 4. 124. Remainder 3. Benefit, I did not use multiplication by anything that wasn't with zeros at all. So I did not need multiplication facts to do this problem. Drawback, if I had to do this 9 times, this would be annoying, right? Tedious, certainly not efficient. Again, one of the benefits, though, is that it allows you to do multiplication when you don't know the multiplication tables. But that would be all of us to some degree at some point. I don't know multiplication tables for 28, right? So there's that.